Hello everybody. Today in this video I'm gonna show you the review for your exam 2, what you already took. I already posted the solution there, but I'm gonna explain that one here so that you can understand that one better. Okay, so let's start. So problem number 1, you can see I already draw the problem number 1 here. So here is your canal and the elevation is 187. Here is the river, the elevation is 121, and if you see the head difference is 66 feet. Okay, so if you see the length, actually how the flow will occur here, so you can see the flow will go like this way, right? Because this is sand and the hydraulic conductivity here is much higher than the other soil. So you can see the length of that flow path is basically 500. So we can find out our I is equal to del H divided by L. So 66 divided by 500, which is basically 0.132. Now the area of flow, this is kind of important. You can see, because your area, cross-sectional area of flow must be always perpendicular to the direction of flow. So this way. So if you see from that side, then basically this is your area. Now this one is asking that for 100 feet length of the canal per day. 100 feet means like this way, length, 100 feet length in this way. So basically your area would be 100 feet multiplied by 0.5, which is actually 50 feet square. Okay, so try to remember that one, that your cross-section area of flow is always perpendicular to the direction of flow. Okay, so that's basically your A here. Now you can see our K is given, which is basically 1 into 10 to the power minus 3 feet per second. Since they asked the answer per day, so it's better to convert your K into feet per day. Okay, so if I want to change that one to second per day, so we can find out this one would be 86.4 feet per day. Now we know that Q, total flow for one day, would be K I A T. So this one is 86.4. Then I is 0.132. Area is 50 and time is 1 day, so this one is basically 570 feet cube per day. So one more thing, because for this exam we had 3 different sets. even though the number was a little bit different, but the actual problem is same. I'm just trying to show you one of them. Okay, the first one, one of them, you can see all those three sets are solution for all the three sets are given in your blackboard. Just try to pick like this one. If you understand that one, then you will be able to do all the other sets. Okay, now let's move forward. Problem number 2, this one is saying that what would be the seepage velocity of water through the sand layer. To find out the seepage velocity, actually we have to find out the Darcy's velocity. And from the Darcy's law, you know your V is equal to Ki, which is, actually we already know K is 86.4 feet per day multiplied by your I, which is 0.0132. So 11.4 feet per day. Now seepage velocity, V seepage, is nothing but your Darcy's velocity divided by your n. So your n value is given, which is 0.3. So if I plug that one here, so that would be 38 feet per day. Okay. Now for problem 3 and 4, actually I'm going to do that one at the end because I have to draw that figure here and that might take a while. So better I do like problem number 5 now and then we'll move forward there. Okay? Okay, so I'm going to show you problem number 5 to 9. I already draw that soil profile here. You can see this is our original ground level. Here is our water level. So this is soft clay and this is medium clay. So this distance is 3 meter, 2.1 meter from here to here is 6 meter, and this one is 3.1 meter. At the bottom we have the bedrock. Okay. So the information they are giving us that the pre-consolidation pressure for the soil pre-consolidation pressure, we write that one sigma C prime, which is 150 kPa. And also your E naught is given, which is basically 0.66. Now they are saying that in future they are planning to add some fill, 5 meter proposed fill. An embankment will be constructed here. Okay, so embankment, and this one will use a soil which has a gamma unit weight is 18 kilonewton per meter cube, and the height is 5 meter. So how much load is going to come from the future one? That's, we call that one actually del sigma prime. Okay, which is nothing actually. If you construct a filling here, and then the pressure that's coming from there is gamma H, gamma equal to 18 multiplied by 5, that's actually 90 kPa. That's not there actually. That will come in future when you construct that one. Okay, so number 5, that's actually asking the expected pressure from the proposed fill is, so that's definitely 90 kPa. That's your answer here. Now number 6 is asking the current effective overburden pressure at the middle of the clay layer. So let's say we are talking about the middle of the clay layer here. So the distance from here to here is 1.55 meter. So the current overburden pressure would be, so we have to add like all those things, you know, like that new construction is not there yet, okay? So we are not gonna count that one now. We are just talking about the current overburden pressure. So this one would be, let's say start from here, so 14 multiplied by 3 plus 17.5 minus 9.8, sorry. And the distance is 2.1 plus the soft clay layer, which is 13.5 unit weight minus 9.8, and the height is 6 plus 15 minus 9.8 multiplied by 1.55. So this one is basically 88 kPa. Okay, so the answer is D, 88 kPa. Now number 7 is asking the total primary consolidation settlement in medium clay layer when the compression index is 0.25 and swelling index is 0.05. Okay, so we have to do a couple of things here. First, try to see that whether the soil is normally consolidated or over consolidated. If it is over consolidated, then we have to check again that after adding this one with the current overburden pressure, whether this one will be higher or lower than the pre-consolidation pressure. Okay, now let's try to do that one, number 7. So first of all, we'll check what kind of soil is that. So I can see my current overburden pressure, which is 88 kPa, is basically less than our pre-consolidation pressure, which is actually 150, right? This means, like in the past, pre-consolidation means like pre, right? So in the past, this soil was consolidated like with a pressure of 150, but currently I have 88. Means like in the past this one was consolidated. Okay, so this is over consolidated soil, so we can just say the soil is over consolidated. So in your book you will see if the soil is normally consolidated, you have one equation for your total primary consolidation settlement. If you have over consolidated soil, then you have two equations there. So I have to check again whether after adding this one, like del sigma prime plus this one, so you can see 90 plus 88, which is actually 178 kPa, and this one is greater than sigma c, pre-consolidation pressure. Okay, so when this one is greater than pre-consolidation pressure, then I have to use the big equation here. So here S is equal to CSH divided by 1 plus E naught log sigma prime C divided by current over burden pressure plus CCH divided by 1 plus E naught log del sigma prime plus overburden pressure divided by pre-consolidation pressure. Okay, so you can see in this equation CS is the compression index for swelling. Okay, this is just the compression index. E naught is the initial void ratio, which is 0.66. we already got that one 88, we got this one 150, and then we added this one is 178. So if I plug all those values here, then you see CS is basically 0.05. H is the height of that particular clay layer we are talking about. Okay, so we are not talking about this one here, even though they have another soft clay layer here, but we didn't ask to find out the settlement on that layer. So we are just trying to focus this medium clay layer. So you can see this is 3.1 meter. If you keep that one in meter, then basically your settlement would be also in meter. If you change that one to centimeter, then your settlement would be also in centimeter. So if you calculate this one, you will just get this one is 4.7 centimeter. Okay, I just changed that one to centimeter. Actually this one was 0.047 meter. Okay, anyway, so the one of the most important thing here is, like, let's say for here they gave you that you are going to make a field in future. Okay, your plan is making an embankment or something, and then they gave you the height of that thing, and then you just try to find out how much stress is going to come here. But many cases you will see they will just asking maybe like I'm not talking about this particular problem, I'm just talking about like there could be something here that you are putting a foundation here, and that size of that foundation, let's say 10 feet, and you're applying a load of, let's say 100 kip load here. Okay, so in that situation, how can you find out your future load here, your future stress here? You already know that one, that like this one would be P by A, means like 100 divided by 10 into 10, that's actually 1 PSF, KSF, sorry. Okay, so you might have to do a little bit calculation here to find out that what is the expected pressure that's coming from the new structure. You usually get that one from a structural engineer. Okay, okay, let's move forward. Number 8 is saying that if the coefficient of consolidation of the medium clay layer is 1 into 10 to the power minus 3 centimeters square per second, how many years it will take to 50% consolidation? Okay, so very important thing is like what would be your drainage length, maximum drainage length. So we know that TV CV, let's say T50, I'll just say 50% consolidation divided by HDR square. Okay, my TV for 50% consolidation is given, and CV is also given. I have to read this one from this figure here. So you can see there is bedrock here. The soil cannot, the water cannot move through the bedrock because bedrock is impermeable. So the only way this one can go in the upper layer. So this is a one-way drainage. Okay, not both ways, one-way drainage. So for one-way drainage, we know HDR is basically equal to H. Means like if you have any soil here, this one has to, you know, go all the way here to get out from this domain, right? So this one is your maximum, you know, like distance to escape the water from the domain, which is actually equal to the height of this layer. So if you plug these values here, so 0.0197, that's given here, and 1 into 10 to the power minus 3 divided by HDR, which is actually 310 centimeter. I'm changing that one to centimeter because this one is also in centimeter, that's why. And then also your T50 will be in seconds. So you can just solve this equation and your T50, that would be equal to 7.3 months. So for 50% consolidation, it's going to take 7.3 months. Okay. Now let's move forward. Problem number 9. This one is saying the excess pore water pressure at a point where the degree of consolidation is 30%. 30% consolidation means like actually we know from the equation that your UZ degree of consolidation at a particular point is equal to UZ divided by U naught. So U naught is the initial pore water pressure at time t equal to 0. Okay, so you know from the theory that as soon as we apply the load, all the load will be taken by the water. Okay, and then the water will be a stress. They will try to get out from there and they will drain slowly, and you will see that some of the load is coming to the soil, right? So at that time t equal to 0, how much load I was applying there. That's actually the load that's coming from the new structure. Okay, we already know this one is 90 kPa. So if I apply this load and then right after application, this pore water pressure would be also 90 because all the load will be taken by the water. So you said this is like 30%, so 0.3 is equal to 1 minus uz divided by 90. So you can see your uz would be 63 kPa. Okay, so this is the most important part here, that how to find out your U naught. Actually, U naught would be always equal to the del sigma prime, because as soon as you are constructing that one, by the time all the load will be taken by the water. Okay, now let's move forward. Problem number 10 and 11. So they gave you this state of stress on a soil element, 145. Okay, for this type of problem, I said they're asking here the shear stress at plane AB is. So to do that, the plane AB, which is given the plane here, which is so if you draw a line here, we know that I have to measure that one like this. Or I can measure that one this way. So this one would be minus 30 degree because I am measuring that one clockwise. Counterclockwise is positive, clockwise is negative. Or this one is actually 180 minus 30. Okay, so if I see what would be my sigma x, that's actually 60, sigma y 100, my tau xy, we know if it is right side is upward, then it's positive. Right, so this one is upward here, so this one is 45 kPa, and your theta is either minus 30, you can just consider, or 150 is fine. Okay, either of that is fine. So now we know shear stress at any particular plane is sigma y minus sigma x divided by 2 sine twice theta minus tau xy cosine twice there. Okay, so this one is 100 minus 60 divided by 2 sine 2 into 150 minus tau xy is 45 cosine 2 into 150, that's basically minus 40 kPa. Actually, most of you did this problem correctly, so I hope that you already know how to solve this problem. And then number 11 is asking like, hey, what is the minor principal stress? Okay, we have major principal stress and minor principal stress. So usually the equation here, sigma 1 or sigma 3 is equal to sigma x plus sigma y by 2 minus plus minus sigma y minus sigma x divided by 2 whole square plus tau xy. So when you try to find out sigma 1 or major principal stress, that time this one is like this. Okay, sigma 1 is this. When we try to find out the minor stress, that time actually sigma 3 would be this minus this. Okay, so if I plug the value here, then you can see this one is 100 plus 60 minus 100 minus 60 so that's basically 31.8 kPa. Okay, now let's move forward. We have one more problem here from and then we also have extra credit. Okay, so number 12. So that's a circular tank, and the radius of that tank is 50. We usually call that one uppercase, and I want to find out at a point here which is actually is 20 feet away from here, and this distance is, let's say, 50 feet. Now this one is saying that the circular water tank will be constructed on a soil that has a unit weight of 128 pound per feet cube. Okay, the empty tank would create a pressure of 1.5 ksf under the foundation soil. Okay, increase in vertical stress at point A when the tank is full. So when the tank is full, then what would be the pressure? Okay, so we know they gave you this one is 40 feet. So you can see, because of the weight of this structure, your sigma is actually, or we usually call that one Q. Q for structure. That's actually given 1.5 ksf. And Q, when this one is full with water, due to water, let's say Q due to water, is actually gamma WHW. So this one is 62.4, 62.4 into 40 divided by 1000. I'm just trying to convert that one to KSF. So that's actually 2.5. So your actual Q under the pressure, when the tank is full, then basically you will see this one is 1.5 plus 2.5, which is 4 KSF. Okay. Now you can see for this particular type of thing, you can see this one is a round shape, like foundation. In that situation, we know that your Z by R, that's actually your Z here, 50 by 50. And your lowercase r by capital R, that's actually 20 divided by 50, which is 0.4. Now if you see the table, then you can get your A prime and B prime from there. So you get your A prime, which is actually 0.32, and your B prime equal to 0.27. So your del sigma change your vertical stress, that would be equal to 4 into 0.32 plus 0.27, 2.4 KSF. Okay, now let's move forward to problem number 13. So that's the side of this foundation. These one are A, B, C, D, E, F, G, H. So they are asking like the change in vertical stress at a point that is just 20 feet below the point A. 20 feet below the point A here. To do that, actually we have to divide this foundation in such a way that A is the corner of each of the rectangular. Okay, let's see how we can do that. So you can see, like, to do that one, we can just extend that point up to G. And extend that one here. So I can write now that del sigma z at A equal to Q into I3. But here I'll just say I3 for ABCD plus I3 for ADEG minus I3 for AHFG. Okay, so the effect of this slab at this corner and the effect of this slab at this corner, but I don't have any slab here, so I have to subtract this part from here. And you can see in all three rectangle A is the corner point. Okay, so I can see this one and this one is same size. So for rectangle ABCD and rectangle ADEG, your M equal to B by Z and N equal to L by Z. You have to always remember that L is always bigger than B. Okay, so here this one, the biggest dimension is actually 40, so that would be your L. And here this one is 20 divided by 20, which is 1, and this one is 2. So if you go to the table, then basically you will find out I3 for these two rectangle is 0.1999. Okay. Similarly, for rectangle AHFG, you get your M equal to B by Z (20 by 20 equal to 1), and your N is also L by Z, which is 20 by 20 equal to 1. So from that two, you get your I3 is equal to 0.1752. Okay, now if you plug those values here in this equation here, then you can see this one is 50, 1999 plus 0.1999 minus 1752 So your answer is 11.23 KSF. Okay. Okay, problem number 14. I just draw that one here. You can see this is two ship piles is inserted into the river. That was actually, this one was the bottom of the river. Then we excavated that one here, okay? And now we want to make, let's say, a foundation here. So what we are trying to do, we just put like that sheet pile here and then pumping the water out there. So this is the current situation, that the water table is inside here and at the outside of the sheet pile is here. Okay. Now this one is asking that if the unit weight of the saturated soil, river soil, is 16 kilonewton per meter cube, means like if the soil gamma D here 16 kilonewton per meter cube, then the effective stress at point A. Okay, effective stress at point A. So first of all we have to find out the total stress, and then we have to find out the pore water pressure. To find out the pore water pressure, actually I need to know the head at any particular point. For our case is A here. Okay, so if I try to do this one here, then basically you can see your H is here from here to here. That's actually 2.5 plus 2, 4.5 meter. Now we have to count how many equipotential drop we are expecting here from this flow net here. So if you count that one here, then you can see first drop, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10. Total drop is 10. Okay, so ND you can remember that all the time when we count that one, we don't count the first one, we start from here because this is the first drop. Okay, from here to here, this is the first drop. Second, third, fourth, fifth, sixth, seventh, eighth, nine, 10. So there will be 10 equal drop for this particular flow nets. Okay, so for each of them, how much is going to drop for each of them? Okay, so equipotential drop that would be equal to 4.5 divided by 10 is equal to 0.45 meter. So basically if I put a piezometer here, then the height of water would be here. Right? Similarly, if I put a piezometer here, you will see a little drop from here to here is drop. How much drop? 0.45 meter. So actually the water will be here. So this one is actually 0.45 meter. Similarly, if this side, if you just put like a piezometer here, then the water will be here. If you put a piezometer at A, you will see the water is actually here, which is actually 0.45 meter. right? You can also see, like here, if you count from this way, so 1, 2, 3, 4, 5, 6, 7, 8, 9. At point A, we have 9 drops. So what would be the head at A? That would be 4.5 minus 9 into 4.5, or 9 into 0.45. That's basically 0.045 meter. Okay, so if you put another one here, piezometer, then basically you will see the water level would be here in such a way that this difference is 0.45 meter. Okay, so anyway, so if you see that one from here and they gave you the distance is 0.9, so I know that the head is here. So actually the pore water pressure del U would be gamma W HW. So you can see the HW is from 0.9 plus 0.45, so 1.35. 9.8 into 0.9 plus 0.45, that's basically 13.2 kPa. Now you find out the total stress here. So total overburden stress at A, that would be gamma soil saturated into H. So that's actually 16 multiplied by 0.9. That's actually 14.4. So effective stress would be total stress minus U. Actually, this is, you can say U here. So 14.4 minus 13.2, that's actually 1.2 kPa. Okay. Now I told you like we are gonna do the problem number 3 and 4 after finishing that one. Okay. So if you see like problem number 3 and 4, I'm not gonna draw the whole thing here, but if you understand that one, then basically you will understand 3 and 4 very easily. So first of all, this one is saying 3 is saying that this is also a flow net problem, that the flow net around a single row of sheet pile in a permeable soil is shown below. If the total rate of seepage through the soil per unit length of the sheet pile is 1.58 feet cube per minute, the hydraulic conductivity of the soil is, so it's just for one unit length of the sheet pile. Okay, so you can see here, if you count that one, then your ND is basically 17 here, and your number of flow channels, that's basically 4. Your H is 260.3 minus 193.3, which is actually 67 feet. And your Q is given 1.58 feet cube per minute. Okay, so we know that Q equal to K H ND divided by NF divided by ND. So your Q is 1.58, K H is 67, and NF by ND is 4 by 17. So if you solve your K, you will get that 1.1 feet per minute. Okay. Now number 4 is saying the pore water pressure at point A. The pore water pressure at point A. So we have to just count how much actually drop is occurring there. So if you count at point A, the number of drop at point A, the number of drop would be 3. So at A, your head would be 67 minus 3 into equipotential drop is basically 3.94. So if you solve that one, then basically you will see this one is actually head drop. Let me write it down here, that would be easier. Head drop that's actually 11.82. Okay, so if you put a piezometer here at point A, so let's say this is your water table here, but you will see this one here, which is 11.82 feet below that thing. Now you can see the distance from here to here is actually 260.3 minus 160.3, actually 100 feet. So the height of the water that would be 100 minus 11.82, which is 88.18. Okay, so your pore water pressure would be gamma WHW, so 62.4 multiplied by 88.18, that's basically 5.5 KSF. Okay, so we are done here. So I'll stop it here, and maybe we'll do some more in future. Thank you so much. Appreciate that. Bye.